Hello developers, let's start developing. My name is Veko and today we're gonna be taking a look at task 15 from the Advent of Code 2021. And to be honest, I've taken a look at this thing and it seems that we have a cavern and we are allowed to move anywhere. We are moving in the left or down, left, right, up, down in the four principal direction. And each cell has something that is called a risk level. We want to go through the grid in such a way that we accumulate the lowest total risk. And for the given scenario, we have that path and that is the minimum. So it's relatively a straightforward task, and that's basically that we need to find the minimal path through a graph, so to say. In essence, this is Dijkstra's algorithm. And we're gonna do some kind of a variant of that. But first of all, of course, we're gonna have to read the input. Let's have this. This is our test input. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns. And of course, it has 10 rows as can be seen. So we just need to read that. We're gonna read the input lines, and we need to split each line on an empty string, and this thing still hasn't relearned. Yeah, I like that. Only I like, yeah, we can use C for character, and each character is parsed on base 10, and then we're returning the lines. Only we're not returning a number, we're returning an array of numbers. A matrix, an array of arrays of numbers. In other words, a matrix. So this will be a matrix, this will be a matrix, and this will be a matrix, and this will be a matrix, and now everybody is happy. Did I change run task? Yes. We can run this. And we should see our 10 columns of 10 items each. So the first one is 1, 1 ends with 2. The last one is 2, 3 ends with 81. 2, 3 ends with 81. So our input is correctly read. Well, yay, that's a victory. Now, what we need to do? One of the things, so this is our input and this is our path. And we are counting only the risk level of the positions we enter, so we're not counting this. And one thing that is a given, that the risk levels are going from 1 to 9. Yeah, so that's what we need to do. So once more I will use the extend thingy, so because that when I can handle the finding the neighbors a bit better. Will this know what I want to do? Well, not that. That will be an array and we will use the input, but we will array of input null length, 0 length plus 2, and we're gonna fill that not with zeros but with something that has a ridiculously high risk level, so that we can be sure that we never go that way. Okay, if you want to have it like that, have it like that. And we'll need to map this. Yep, actually let's let's have this as a constant. So we're gonna surround ourselves with that. Let's just see that we're doing okay. Console.log extended. Actually, I'm not even gonna take a look at this because it is something other. So I will say print matrix, because we're gonna need to print a lot of matrices, and I'm gonna print so each cell, and if the cell equals ridiculously high risk level, then print out that, otherwise print out C. Yep. And if we're correct, we should get our 10 by 10 array surrounded by hashes. Yep. Okay, that's it. So we're going to say that we are starting at position x is 0 and y is 0. We're starting at that position. And we're gonna say and I'm gonna do a bit of brute forcing on this. Let's calculate all the minimum risk positions for each item. That would mean, what is the minimum amount? Let's use Excel to solve this a bit. Now I want to do again text to columns and fixed width, and I want to split on each of those values. Let's zoom in a bit, let's compact it a bit. Let's add a tick border so we can see it better, and let's copy it over here. So what I'm gonna do is basically put in, let's put 999 all over the place here. Just a tiny bit more. Let's have it border. And now we're gonna say, for this one, the price to get, the risk to get here is 0. So what is the risk to get here? Well, it's the minimum of any neighboring plus its own value. So at the moment it's this one, and so I'm gonna say 0, and I'm gonna mark these two that they need to be processed since I've changed this. So I'm processing this, and it's the minimum of everything around it plus its value, so that is okay. And I'm saying, okay, this one is processed, but please process my neighbors. So this one is 6, the minimum value will be 7, and again, please process my neighbors, and so on and so forth until we get to this one. Yeah, that makes sense. So that is the algorithm that I'm gonna use. I was just want to say these two numbers. Yeah, the height and the width of our input, so that we know where we are going. So we're gonna create another matrix, and that matrix will be basically a copy of the input. And thinking of that, yeah, let's try. Actually, let's comment this out. I might revisit this idea, and actually I will do this. So let's create a new array. So risk level is right now a matrix that has the same structure, number of columns and rows and everything, as the input. The only difference is that it has only this value. And since it's 10 by 10, so we have 100 cells. Even if we went through all of them, 100 times 9 is 900, and all of them were 9s. 100 times 9 is 900, so we could not theoretically have reach anywhere near the ridiculously high risk level. We'll see if this holds for the real input. The real input is a bit bigger. So it's 100 times 100, 10,000. Yeah, we're gonna need a few more 9s here. I'm guessing that this won't be a problem. We can always add a few more 9s. So we are making that, and then we're gonna set that the first risk level is 0, and I'm gonna set a queue, and that queue will have only, yeah, you know what, I'm gonna use tuples. They're kind of better at this. So the position will not be this, the position will be this. And let's be formal, the queue is a number array. Yeah, so the queue is all the items that I'm supposed to process next. Yeah. And this is our current position. Now the queue can be literally empty. And I can say, well, yeah, let's have it like this. The cube can have the initial position, and then I will, so that is the position that we need to check. I have no idea what this thing did, but I have a feeling that it's very similar to what we want to do. That means take X and Y out of the queue. See what the risk is. We are getting the risk level for the position. We're calculating the new risk. No, that is not something that we are doing. So we're getting the new risk, and the new risk is that and that. Then for each of the 4 neighbors, up and down. We're gonna have to check. So, yeah, something like this. And I'm gonna separate it because this looks better. So, if x is bigger than 0, then we do have a left neighbor. And for the left neighbor, we're gonna get its risk level and gonna see if its risk level is bigger, is its risk level, current risk level, if it's bigger than its value plus the current risk from, yeah, and our current risk, then basically what we're gonna do is gonna set it to that value and we're gonna add that thing into our queue. So for the right, height -1, we are kind of good doing this the other way around, but I'm gonna use Copilot first. Yep. Because moving on the Y is moving us left and right. And this should be it. So this is left and this is up and this is right and this is down. Yeah. And then we just need to return this. So we're just gonna process all the risk levels, whether we need them or not, and then just display them. For a 10 by 10 grid, this should be relatively simple. And we might get, yeah, 40. Let's see how long it takes, because this approach is linear with the number of nodes. So for 100 nodes it takes 1 milliseconds. For 10,000 nodes, well, I guess it should take around 100 milliseconds. One way to find out. $537 and runtime of 24 milliseconds. I'm gonna take it, and I have no idea whether that's the right answer, but it is. On to part 2. Okay, looks like we have quite a description to read. I have no idea what part 2 is, only I did some discussions and people told me, yo, part 2 is hard. Let's see. Now that you know how to find low-risk spots in the cave, you can try to find your way out. The entire cave is actually 5 times larger in both dimensions. 25 times. Scant is just one tile in a 5 by 5 tile area that forms the full map. Your original map tile repeats to the right and downward each time. Eh? So it goes 8, 9, 1, 2, 3, 9, 1, 2, 3, 4, 9. Okay. I got it. So if we had a map with a single 8, so if our input was a single 8, we need to create 24 more tiles, and each tile is shifted by 1. Okay. 315. Yeah, this starts on 1 1, so then we have 2 2, we have 3 3, and we're gonna have 4 4 somewhere, and we're gonna have 5 5. Yep, and it's shifted. So 0 is not an item, we're not shifting to 0, we're shifting to 9. 9 plus 1 equals 1. Yep, what I'm gonna do, and then we run basically the same algorithm, only we might need, okay, the risk level is, the maximum risk level we got is 537. Let's take a look at actually the risk levels that we had for our full thing. For each character, we'll just do something like this. Oh, this is scary accurate. Yeah, we're getting 3-digit numbers most of the time. And this has 0, 7, 8. So we have relatively low digits, 537, and so on and so forth. This is very much suboptimal because we are not looking for a minimum path. We are looking for all the paths and then just taking the minimum value. There are much better algorithms to do that, using Dijkstra or using A-star searching, but yeah, this seemed to work. Let's see if it will work if the input is 25 times bigger. So first thing that we need to do is actually make the input 20 times big, 25 times bigger. And it seems that if we had the extended variant, we wouldn't have to do these conditions. And I sometimes hate them, but this time I said, okay, I will take them because I'm using a while loop to parse this and I'm not using a for. So if you go extended and for, then it's much cleaner. But this time, since I'm using a queue to process all the points, it's okay. And in essence, we can transform this queue into a priority queue using some kind of a metric, and that would transform our algorithm into an A-star algorithm. And we're gonna run much less in complexity, but for 20-ish milliseconds I'm okay. What I'm scared is if we scale this 25 times more, will it scale linearly or will it scale quadratically? So will we have something that is 20 times slower, which will be half a second, or something that is 400 times slower, which is a bit more? But one way to find out. However, whatever we do, we're gonna have to generate the real input. That is the full, I guess this was a cave. Yeah, cave. So we need to create something. We need to calculate the offsets correctly. So this will basically be something like this is input, and then we have input plus 1, input plus 2, input plus 3, input plus 4. Yeah, I know this is totally illegal. Nope. And then we're taking input plus 1 up to 5, up to 6, up to 7, up to 8. So if we have 1 here, we will have a 9 here. And if we have an 8, this is a 9, this is a 1, this is a 2, this is a 3, this is a 4, this is a 5, this is a 6, this is a 7. Am I correct? 9, 1, 2, 3, 4, 5, 6, 7. Yeah. So what we need to do, and right now full cave will be something like an array, an array, an array, an array of arrays of arrays of arrays. And that is too complicated even for me. Yes, something like this and this. So full cave is a matrix of matrices. Well, yeah, why not? Let's create a method called offset, and that takes 2 parameters. That takes a matrix and returns a matrix. Okay. Something like this. Take each element and map it using an offset. Yeah. Let's see how smart Copilot actually is. Input 2, 3 and 4. 1, 2, 3, 4. Well, not really. And I'm gonna align this because I'm gonna mess something up. Yep. 2, 3, 4, 5, 6. 3, 4, 5, 6, 7. And up to 8. 2, 3, 4. Ending with 4, ending with 5, ending with 6, ending with 7, ending with 8. Yeah, this is okay. So, once we have the full cave, that's what we want to do. The full cave is a 5 by 5 matrix, and we want to actually mesh everything together. We cannot flatten it. Nope. So we can have a, I'm quite sure that there's a more efficient things like more efficient way than this, because now I'm gonna add another for loop. Yeah, I'm gonna call that a piece. something like this. And of course we're gonna need to add rows to full cave each time that we want to. Actually we can initialize it. Let's take the width and the height. Yep. So this is an array full of zeros, and this is stupid what I'm doing. No, what I want to do is actually simple two ways. So then we have the row index and that goes, sorry, I did something that I didn't intend to do. That goes from 0 to 4. And then this goes from 0 to 4 as well. And for each item, full cave of that value, no, full cave not on that value. Yeah, this is wrong. So for each of the 25 items, which is an array, the index in full cave, yeah, just a sec, this should be times 5, and this is again times 5. Okay. So our index will be the row index minus 1 times the height plus our x, and the y index will be the column index minus 1 times the width plus y. With this minus 1 is how many full sets or full tiles we are following. So if we are the third element of the fourth tile, we need to count that we have 3 full tiles in front of us and then add our item. And then we need to save something like this. Full cave of x index and y index is actually the input of x and y, and we're gonna need to offset it by the index plus index, because that's how it goes. This is 1 0 and it's offset once. This is 2 0 and it's often offset twice. This is 1 1 offset twice. 0 2 2 0 actually, this is 0 2, and it's offset twice. And you can see that we have diagonal lines actually running. So each of those diagonal lines have a constant sum of x and y, and we're gonna need to check our offset method. It takes a number. a simple number and an offset that is another simple number and returns a number. And I'll keep that as a method so that I don't do anything weird with it. So we're not gonna use this. We have just one quadruple for cycle. What can be bad about that? We're just gonna say return value plus offset for now. And let's see what happens if our input is 8, literally 8. Yeah, we don't even need that. Whatever, print whatever you want. Actually, let's pad it to 2 characters with spaces. Let's see if we get what we actually saw before. We're not going to. Cannot set property -1 of undefined. What is -1? We get 0 -1. Okay, I'm stupid. We're not counting from 1, we're counting from 0. So the 0th index will return 0 for this. So we don't need the -1 thing. If we started counting from 1, we would have needed the -1 because the first one, yeah, we got some values and those values are quite dissimilar to what we actually needed. So no, they are quite correct, only we didn't wrap around the 9. And now we can add that, and that will need to be added here. Value plus offset. If result is bigger than 9, how this thing doesn't wrap correctly, because this wraps, it only has 9 valid values. It doesn't have 10. It's not from 0 to 9, it's from 1 to 9. So if result is bigger than 9, we will just gonna take 8 out of it. And since the maximum offset that we have will be 8, 1, 2, 3, 4, 1, 2, 3, 4, this cannot get much bigger. So even if we started with 9, this would be get up to 8 here. So we would each of the values that are moving through the matrix, through the 5 by 5 tiles, will basically jump the 9 only once. So we will not have a situation when offset is, for example, 20, and then we are just removing 8 and getting the wrong value. It's exactly 5 by 5 tile, so I'm gonna abuse this. So this is not a good algorithm for the general case. Okay, why am I doing this to myself? We forgot to return result. So if result is bigger than 9, return result -8, otherwise just return whatever the result is, because it's not bigger than 9. We're gonna need to take out 9, because if it's 10, we want 1, we don't need 2. And this is why I made this into a separate method, so that we can mess around with it if we want to. Why aren't you finding that? Yeah, 8, 9, 1, 2, 3. If we look for the third line, yeah, I have some extra spaces somewhere. So that's cool. Looks like it's correct. Now let's go back to our 10 by 10 example and just say write out the full cave and mash everything together. Let's see if this is what we want. Yep, we got a match. So we are totally matching this 10 by 50 by 50 grid. So now we need to run our code once more. And actually, since we're doing this and this, we can just process a cave, and this will be a cave. I will make it into an arrow function. That part is easy. Let's have it here. So whatever cave we have, we are getting the width and the height, we are creating the risk levels, we're processing something, we don't have to print it. Actually, we can do this. If we're debugging, print the matrix out, and I will add a second parameter, debug, which is a boolean value which can by default equal to false. That's okay. So we've got our full cave, and let's see what happens when we say return process cave on the full cave. We are defining the actual debug value. So result part 2 is 315, and we got it in 50 milliseconds as opposed to 9 milliseconds. So that's just 6 times less. Yeah, so hooray for brute force. And 315 is the correct answer. Let's see what happens when we have our 100 by 100 that we're gonna transform to a monstrosity with quarter of a... This has 10,000 items, so we will transform it to something that has 20 times more items, so that's quarter of a million items. And I should not have told it to write itself out, because I think most of the time in these 2.5 seconds were spent writing that input. So now I can always say, well, don't write yourself out, even in debug mode. (770 milliseconds), which is more than acceptable, and let's see if this is maybe the correct answer. Yes, that's the correct answer. And we have 30 stars so far. Well, to be honest, the second part, the hardest part for me on the second part was basically multiplying the grid and transposing it using the offset. But other than that, our original silly algorithm, so to say, our algorithm that is basically calculating all the minimum paths is running fast enough. So yeah, this is our second slowest task, still 730 milliseconds even in non-debug mode, and it's basically 26% of all the processing, but still our champion is task 12 part 2. In task 13 we have somewhere a forgotten console log, which takes us a second and a half. Well, we'll get to it if and when we need to optimize it. So far it's 2.8 seconds for the whole batch, and to be honest, this is not something that I'm too worried about. So that is about it. Thank you for watching and join me tomorrow for task 16.